Hey, everybody. I wanted to do an example here of, in the last couple videos, we've been looking at lines and planes, but let's do a little bit of work with them so we can get a little more used to them and hopefully understand them a little bit better. So I've got this question. I've got 2 points. Let's name these points. I'll call them A and B. There's a line through them, and I want to know where that line intersects the plane that's given here, okay? So let's start by addressing this problem mostly algebraically, but maybe I'll use this as an opportunity to remember how we construct a line given 2 points. So let's say I have my points out here. All right, I'll call this one B and this one A. So here's my origin, right? So I'm imagining drawing an arrow, a vector from the origin to B, and a vector from the origin to A. So, sorry, this second one shouldn't be to A. What we're gonna do, there's a few pieces to this. We're gonna use, we're gonna use our points. I can't get this right. We're gonna use our points to create a direction vector. So it won't really matter which direction we go, right? So I'm going to just draw it this way. And then we imagine the line through these 2 points, right, is going to go along this direction vector. And if we have a vector out here that points at any other point on this line, so we'll call this R0, and this is the vector R. This vector R is going to point at any point on this line. And the way we get it is I'm going to have a scaled version of this vector, the red vector. Okay, let's call that red vector V. Then this blue vector can be a scaled version of V, right? And so by changing the scaling on that vector, we can hit any point on this line, right? I make V bigger and it gets through all these points. I make it smaller, it starts hitting the points closer to B. If I make it negative, it starts going in the other direction, right? And so it's pretty straightforward from this picture to see that R is equal to R0 plus TV. Okay, so we just need to figure out what R0 and what V are. R0 is easy enough. We can choose either of our points. It's pointing at one of them. I happen to choose B. So R0 is just going to be the vector 0, 1, 1, right? Pointing at the point B. V, the way I've drawn it, and I'll just stick with that, is going to be the vector from B to A. So that will look like the vector 1, -1, -3, right? I take the coordinates of A and subtract the coordinates of B. It's sort of saying, like, how do you get from B to A? I have to go 1 unit in the X direction, -1 unit in the Y direction, and -3 units in the Z direction. And that gives me my vector V, okay? So now I've immediately got my vector R. It's 0, 1, 1, or I should say my vector function, 1, -1, -3, right? So I'm just copying R0 and V into this formula. I'm going to write this as, in component form, as it's going to look like T, 1 minus T, 1 minus 3T, right? I'm just using the definitions of vector addition and scalar multiplication to come up with this, okay? So we've still got a lot of work to do, but we now at least have an equation, a function that represents the line that we're actually interested in. So that seems like a very obvious first step. If you're asking a question about some line, we should have an equation for that line or a function for that line. Okay, so what next? Well, let's imagine the situation. So here's the line we've just defined, right, through these 2 points. Somewhere out there, there's a plane, right? So it's extending in all directions, but I've just drawn a little piece of it. And this line that we're defining with this vector equation hits it somewhere and carries on, okay? Now, what does it mean to say that this vector line, or this line defined by this vector function, intersects this plane? Well, it means they share a point, right? There's a point on this line that is also a point in this plane. Well, what does it mean to be a point on the line? To be a point on the line means your coordinates are given by some value of t, right? There's a value of t. If you take t to be all of the real numbers, one of those values of t spits out xy coordinates. So sorry, let me say this a different way. For every value of t, this is a point on that line, okay? Right? So here's the vector pointing at it, here's the coordinates. We're looking for the one that also lies on the plane. What does it mean to lie on this plane? It means you satisfy the equation, point on the plane, satisfies 2x plus y minus z plus 3 equals 0. That's what it means to be a point on the plane. Your coordinates, x, y, and z, when put into this equation, make it true. Well, the point in question has these coordinates, t, 1 minus t, 1 minus 3t, right? So what we're going to do is just put these coordinates into this plane equation and find the t value that makes them true. In other words, this is my x, this is my y, this is my z, right? So I get, just replacing x with the x equation in t over here, I get 2t. Y is 1 minus t. Z is 1 minus 3t plus 3 equals 0. And then we just do algebra. So I've got 2t plus 1 minus t minus 1 plus 3t plus 3 equals 0. What do we have? 2t minus t is t plus 3t. I've got 4t plus, and I've got 1 minus 1 plus 3. So 4t plus 3 equals 0, which means t equals negative 3/4. Okay? So what does that mean? That's telling us that at the t value, negative 3/4, which spits out the points, so at t equals negative 3/4, r is equal to, and I'm just putting in t equals negative 3/4 into our equation, 3/4, 1 minus negative 3/4 is going to give me 7/4, and then 1 minus negative 3 times 3/4, so 1 plus 3 times 3/4, 4/4 plus 9/4 gives me 13/4. Right, so I just put this value of t into this equation. In other words, this r is pointing at a point that satisfies the equation for the plane, right? If we take these values of x, y, and z and put them into the plane equation, 2 times negative 3/4 plus 7/4, right? There's my x, there's my y, minus 13/4 plus 3 equals 0. What do I get? I've got negative 6/4 plus 7/4 minus 13/4 plus 12/4 equals 0. Is this true? It is, right? We've got a positive 1/4 here, so there's a total of 13/4. Adding in the 12 minus 13/4 gives us 0, and this equation is true. So we are indeed pointing at a point that satisfies the plane equation, right? Which means pointing at a point means it's on the line, because that's what this vector function does. It points at points on the line. Satisfying the equation means it's a point on the plane, because that's what it means to be on the plane. You satisfy this equation. So let's take one last look at this with a little bit better graphing. Let's see. So here is, oops, maybe I'm not quite sharing with you. Let me make sure I'm sharing the right thing. Let's share this. Okay, so here are the 2 points in question. What we found was the line through them. That was our vector equation. Here's the plane, right? And so we can see where that intersection point is. And here is the point C, which has coordinates, right, over on the left-hand side here, exactly what we said, -3/4, 7/4, and 13/4. And we can see that that is where that line hits the plane, right? So I think this is the correct orientation in terms of our standard orientation. The red is the X, the green is the Y. We can see what this line looks like. It's a little hard to tell where the plane is until you start moving it around a little bit, but we can see that intersection there. Okay, that's it for that example. I'll do a few more examples like this in other videos. Thanks everybody. See you next time.